Am I audible?
Yes, ma'am.
Okay. So we had left off at chemical shift. Okay. So we'll be starting with that again. Just a minute. I need to share my screen now. So we're going to discuss the factors affecting chemical shift. We were discussing NMR spectroscopy. So today we have quite some portions to cover. We'll be covering NMR. We'll be looking into mass spectroscopy, and if time permits, I will also be explaining about fluorescence and phosphorescence. Okay, so let us finish up with the remaining portion for the NMR spectroscopy. So there are various factors that can affect chemical shift. Okay, so you can have, already we have discussed about what are the factors, like hydrogen bonding can affect, electronegativity of substituents can affect, carbon hybridization can affect. So we have seen some of these effects affecting the IR spectra as well. There are some other effects like magnetic anisotropy, local diamagnetic effects, and also the magnetic fields that are generated by neighboring atomic groups. Now, what is this anisotropy? So, anisotropy is essentially different properties generated by changing the axis or changing the geometry. So the properties are not same along all the axes, they're not same along all the geometries. Along with the change in the geometry, the properties change as well. So what is magnetic anisotropy here? So this is mainly affecting benzene. So we have seen that benzene protons are highly de-shielded. So why does that occur? Okay, why does that occur? Now, anisotropy effects are majorly seen in aromatic compounds as well as in acetylenic compounds. Okay, acetylenic compounds. So let us see what happens here. We have seen how if you have a nucleus and the magnetic field is there, it is placed in the magnetic field, the circulating electrons have their own magnetic fields which can cause shielding or de-shielding, right? So what happens in the case of benzene is that, suppose you have a benzene molecule, you can see the geometry here. So this diagram, please be careful about this. So the magnetic field is upwards, right? The magnetic field is upwards. Now we want to see the shielding or the de-shielding effect on these protons. These are the ring protons. Okay, these are the ring protons, and we want to see the effect of the magnetic field. Now, because of the ring, okay, because of the ring, the pi electrons within the ring are also circulating. Okay, they are also circulating. So this is called a ring current. Okay, this is called a ring current, and it is like a loop of wire. Okay, this is just designed to flow in this particular direction. And this particular direction, when we are seeing the geometry, this ring current is flowing in this direction, the magnetic field is in the upper direction, and because of this loop, the electrons are flowing like this. Electrons are also flowing around the ring like this. So because of this flow at the particular proton, what is the direction? What is the direction? This is up. Okay, this is up. So they are de-shielded by the diamagnetic anisotropy of the ring. Okay, they are de-shielded by the diamagnetic anisotropy of the ring, because in the magnetic field is upwards and the circulating pi electrons are there. So the secondary magnetic field which is generated by the circulating pi electrons, it is actually de-shielding the aromatic protons. Okay, it is de-shielding region के अंदर वो आ जाता है. So protons are just, they happen to lie in the de-shielding region, so they are being de-shielded by the circulating pi electrons, and this is because of the geometry. Now what happens in acetylene? हम लोग anisotropy के बारे में बोल रहे हैं, that along with the axis, the shielding or the de-shielding is happening. So if acetylene molecule, it's suppose you can imagine it like a plain one, or you can imagine it like a cylindrical. So it can be linear, but it can be linear along the x-axis, or it can be linear along the y-axis as well. So here in acetylene, the magnetic field is generated by the induced circulation of the pi electrons. Okay, by the pi electrons, and it is such a geometry that the acetylenic hydrogens will be shielded. Okay, so they will have resonance at higher field, they will have resonance at up field. You know that shielded means upfield. Okay, so protons falling, if it is within the conical area which is there for hydrogen, then these are shielded, and those that are falling outside the conical region, those will be deshielded. Okay, similarly for acetophenone and for rigid six membered rings, these shielding deshielding happens differently because of the zones that are created by the circulating electrons, circulating pi electrons. Okay, now we come to equivalence. Okay, we come to equivalence. Now, what is chemical equivalence? How can we say that the signal for one proton will be influenced by another proton? And when can we see that the signals will be same nature for some kind of protons? Now, if two protons are in the same chemical environment, and if they can change as a result of a symmetry operation, it is the chemical equivalent. Now, see this particular portion, CH2, Cl2. Now, these two protons, what are their immediate environment? The two chlorine atoms are there. Both of them are attached to the same carbon. Okay, so they will give the peak in the same location. They will not shift. For example, if I label this particular H as HA and HB, they will come to resonance at the same position because their chemical environment is the same. Okay. On the other hand, what is magnetic equivalence? For chemically identical nuclei to be magnetically identical as well, the nuclei have to interact with each other. Okay, they have to be interacting with each other. Now here you can see that these protons, they will not be magnetically equivalent. Okay, they will not be magnetically equivalent because they will have to interact with two chemical equivalents in the cis and trans position. So whenever the geometry is like this, that they are in the cis or trans position, they will not be magnetically equivalent. Now, according to the chemical shifts and the chemical or magnetic equivalence, we have a spin-spin splitting. We are going to see the splitting. So whatever NMR spectrum you see a lot of split peaks. So those can give information about what types of hydrogens are there, what type, how many number of hydrogens are there, and how many types are there. So here you see, now suppose you have 112 trichloroethane. Okay, now this CH2 group is under the influence of what? Chlorine. The next carbon is attached to a hydrogen. So this protons, whatever protons are there, they are influenced by each other and they will split. Their signals will split. So now how many signals we can see? For this proton we will see, and for these two protons we will see in another position. Okay, so essentially we will have two peaks, right? We will have two resonance positions, one for this one for these two. These two will come together at one particular position. Okay, but instead of seeing two single peaks, we will see split peaks. Okay, we will see split peaks. For example, now this spin splitting, one proton can be split by the neighboring proton, and depending on the number of hydrogens on the neighboring carbon, suppose number of hydrogens on the neighboring carbon is n, then I will get n plus 1 peaks. Okay, I will get n plus 1 peaks. Now suppose consider this particular hydrogen, the one that is attached to the carbon containing 2 chlorine. Suppose I'm going to consider this hydrogen. What is the number of hydrogens attached to the neighboring carbon? 2. Okay, 2. So this signal for this particular hydrogen will split into 3. Okay, it will split into 3. So I will get a triplet for this hydrogen, and I will say that this is a one hydrogen triplet. Okay, this is how you denote it, one hydrogen triplet. Now consider these two protons. They are considered to be chemically equivalent, and they are going to come into resonance at a single position. Okay, single position. Now instead of one peak, how many splitting will be there? See the neighboring carbon. How many number of hydrogens are attached? 1. So this particular signal will be split into 2. This will be split into 2 and it will be a doublet. And how will I term it as? It will be a 2 proton doublet. Okay, it will be a 2 proton doublet because the 2 protons are coming into resonance at a single position, but their signal is being split into 2 by a neighboring hydrogen. So how many peaks total? It will be 5 peaks. A group of 3 peaks or a triplet at 5.77 ppm, because this particular proton, which will be a triplet signal, has two chlorine atoms, two electronegative substituents, so this will be deshielded. On the other hand, this particular two proton signal split into two, which will be a doublet, it is relatively attached to this carbon and this chlorine and does not have immediate attachment to another electronegative atom, so this will be relatively upfield. Okay, so this is how the signal will look like. Okay, this is a real NMR signal. So this is how the signal will look. You have a triplet here and you have a doublet here. Okay, the intensity of the doublet is higher because it is a two proton doublet. Okay, it is a two proton doublet. The splitting here is triplet, but the area also is less because it's a one proton. Okay, it's a one proton triplet. So here you can see further examples. What kind of associations are there so that you can calculate the number of protons. Okay, how many number of protons are there? So this is just example of what we have already discussed. Suppose you have CH3, CH2I. Okay, ethyl iodide. Suppose you have ethyl iodide. Now the CH3 protons, they will come into position. One first position they will come. Similarly, the CH2 protons will also give another signal. So how many signals you will have? You will have two signals. Okay. Now how many peaks will it be? For the CH3 protons, the neighboring carbon has two hydrogens. Okay. So how many peaks will it be? Triplet. Okay, you will have a triplet, so this will be a three proton triplet. Okay, this will be a three proton triplet. Similarly, for the CH2 protons, they are also coming into position, into another resonance position. How many peaks will they be split into? See the neighboring carbon, how many hydrogens are attached? 3. So 3 plus 1 is equal to 4, so it will be a 2 proton quartet. Okay, it will be a 2 proton quartet. Here it is explained. Okay, CH2 and there are 3 protons, so 2 proton quartet. Now where will be the positions? CH3 is attached to just the carbon. Okay, it is attached to just the carbon, so this will be shielded, it will be upfield. So the triplet arising here will be upfield, as you can see in the diagram here. Similarly, for CH2, which will be a quartet, it will be deshielded because it is attached to iodine. It is directly attached to iodine. Okay, so here you can see the example. More examples are discussed here. Okay, more examples are discussed here. Suppose you have two methyl groups. Okay, suppose you have two methyl groups, you will have a 6 proton doublet because the adjacent carbon just has one hydrogen. Okay, you can have a 6 proton doublet. Okay, and if you have 6 equivalent neighbors, you can have a septet. Okay, you can also have a septet, a 1 proton septet. So this is the different kinds of cases that can happen. So now why this kind of spin splitting is arising? Because they can sense one another. They can sense, suppose you have two carbons, Ca and Cb, and Ca में Ha attached है, Cb में Hb attached है. Now hydrogen on carbon A, they can sense the spin direction of the hydrogen on carbon B. Okay, they can sense the direction. And in some molecules, hydrogen on carbon B may have spin plus half. In some other molecules of the solution, hydrogen and carbon may have spin minus half. Okay, they may have minus half. So this can be a X-type molecular situation. This can be a Y-type. Now the chemical shifts of the proton A will be influenced by the direction of the spin, and it will be coupled to proton B. Its magnetic environment will be affected whether it has a plus half or a minus half spin state. Okay, so proton A will absorb at slightly different chemical shift value in type X than in type Y molecules. For example, in X-type molecules, okay, X-type molecules where the directions are the same. Okay, if the directions are aligning the same, proton will be slightly deshielded because the field of the adjacent proton will be aligned with the applied field. So the magnetic moment will add to the applied field. In Y-type protons, proton will be slightly shielded because the field of the proton B will diminish the effect of the applied field on proton A. Okay. Now, if you have a heteroatom, OH, NH, SH, those signals remain unaffected. OH का signal जहां पे आना है उसका वहीं पे आएगा. The chemical shift will be the same. Okay. CH3 fluorine, CH3OH, CH3Cl, CH3Br, CH3. So whatever may be in the neighborhood, okay, whatever may be in the neighborhood, they will not be affected. Their chemical shift, the protons attached to a OH group, those will not change. Okay, those will not change. Now we can see like spin splitting, how many peaks are there, we can find out. What will be the intensity ratios of the multiplets? They can be followed by from the Pascal's triangle. Okay, they can be followed by the Pascal's triangle. So this is kind of how you generalize. So if you have a singlet, you have 1. Okay, suppose the relative intensity is 1. As soon as you get a doublet, it gets split into 1, 1 and 1. So in a doublet, the intensity will be 1:1. Okay, it will be 1:1. As soon as we get a triplet, in a Pascal's triangle क्या होता है, 1 plus 1 वो middle बन जाता है, and the other they remain the same. So 1:2:1, that is the relative intensity. Okay, for a triplet, the relative intensity will be 1:2:1. For a quartet, again, 1 plus 2 is equal to 3, 2 plus 1 is equal to 3. So for a quartet, it will be 1:3:3:1. Similarly, for a quintet, and so on. And this will be the multiplicity. You can see the relative intensity. So anyone asks you a question on relative intensity, you can easily find it out from the Pascal's triangle. Okay, you can find it out from the Pascal's triangle. So this is an example of how you can find it out. Okay, the relative intensity for a triplet will be 1:2:1. For quartet, it will be 1:3:3:1. Now, this is another important aspect of the spectra, that is the coupling constant. Now, what is the coupling constant? Now, you have triplets, okay? You have triplets, adjacent peaks in a simple multiplet. It can be triplet, a quartet. So, what is the distance between the adjacent peaks in a multiplet? That is known as the coupling constant. Now, what is coupling constant? Does it signify? It means how strongly a nucleus will be affected by the spin states of the neighbor. Okay, it is a measure of how the nucleus is affected by the spin state of the neighbor. And the spacing between the multiple peaks is also measured on the same scale as the chemical shift. Okay, it is also measured as the same scale as the chemical shift. So the coupling constant is always expressed in hertz. Okay, it is always expressed in hertz. So you can see the example here. Here is a triplet. Distance between the peaks is 7.5. Okay, you can measure it in terms of hertz. Now, if you are integrating the peaks in the spectrum, you can also have an information about the number of hydrogen in the molecule. The area under the peak also matters. As we have seen in the first example, area under the peaks will be proportional to the number of protons to which the peak belongs. So you can have a 1 proton sextet, a 1 proton septet. ठीक है, so if it is 1 proton, उसका area जो भी है वो कम होगा. ठीक है, and even if you have a 6 proton doublet, तुम्हारा doublet है, मतलब splitting कम है, लेकिन the area will be very large. Okay, area will be very large. So we can easily find out how many numbers of protons are there by seeing the area under the peak. Okay, we can see the area under the peak. Now let us just check for ethanol कि हम लोग how can we find out the NMR spectra. So CH3 CH2 OH है. So CH3 will be affected by CH2. So it will be a 3 proton triplet. यहाँ पे 2 protons है affected by 3, so this will be a 2 proton quartet and OH का अलग एक सिग्नल रहेगा. So यहाँ पे जैसे कि है ट्रिपलेट हमने पता कर गया. So 3 प्रोटॉन का एक ट्रिपलेट है, so इसका इंटेंसिटी क्या रहेगा 1:2:1. 2 प्रोटॉन्स का एक क्वार्टेट है, यहाँ पे जैसे लिखा Q, 2H. This is how you write the notation. Triplet 3H, quartet 2H, and you also write the peak intensity 1:3:3:1, and the picoproton C attached to heteroatom, so it gives a single peak. So this is how the spectra looks like. यहाँ पे आपका ट्रिपलेट आ गया, क्वार्टेट अगेन यहाँ पे है, एंड एकदम डीशील्डेड एक प्रोटॉन है हेटेरोएटम का. आई एम जस्ट गिविंग यू 1 minute. आप लोग खुद ड्रॉ करने की कोशिश करो. ड्रॉ फॉर एथेनॉल इन योर शीट्स. जस्ट टेक 1 minute, अंडरस्टैंड दिस, एंड खुद आप ट्रिपलेट और क्वार्टेट ड्रॉ करने की कोशिश करो. जस्ट गिविंग यू 1 minute. Okay. Now let us find out the solvents used in NMR spectroscopy. अब जो सैंपल है उसको हम लोग कैसे स्पेक्ट्रोस्कोपी के लिए देंगे? कोई सॉल्वेंट में उसको डिसॉल्व करने के लिए चाहिए. सो व्हाट इज द काइंड ऑफ सॉल्वेंट दैट यू कैन यूज? सो इट शुड हैव अ लो बॉइलिंग पॉइंट, केमिकली रिएक्टिव नहीं होना चाहिए, और इट शुड बी नॉन पोलर, और प्रोटॉन्स नहीं होने चाहिए. अगर सॉल्वेंट में ही प्रोटॉन्स हुआ तो उसका भी पीक आ जाएगा. सो वी विल गेट अ वेरी डिस्टॉर्टेड spectra. इसलिए it should not contain any protons. So what kind of solvents are generally used in NMR spectroscopy? Deuterated solvents. Okay, deuterated solvents मतलब hydrogen is replaced by its isotope deuterium. ठीक है. So जैसे CdCl3, क्लोरोफॉर्म का इक्विवेलेंट हम लोग सॉल्वेंट ले लेंगे CdCl3. DMSO यूज करते हैं, DMSO की जगह पे हम लोग D6 DMSO यूज कर देंगे. ठीक है. एसीटोन की जगह पे D6 का एसीटोन यूज कर देंगे. ठीक है. तो CH3OH नहीं करके हमारा CD3OD यूज कर सकते हैं. ठीक है. और अगर इनफैक्ट यू कैन ऑल्सो यूज D2O और हेवी वाटर. ठीक है. Now there are some kinds of reagents that are known as chemical shift reagents. ठीक है. chemical shift reagents. So अगर बहुत ही क्लोज पीक्स हो गए कि पता नहीं चल रहा है कि मल्टीप्लेट है लेकिन कितना पीक्स का है, how many peaks are there, बहुत सारे पीक्स अगर एक साथ आ गए, then you have to separate them out so that you can see कि कितने पीक्स है and how much is the distance, what is the area. So for that you have to either increase the field strength or use some kind of chemical reagent. Chemical reagent क्या करेगा? उन signals को space out कर देगा, so थोड़ा उनका location change कर देंगे. So what are these chemical shift reagents? Those are rare earth elements. Okay, rare earth elements like lanthanides, and these are used in the complexes found by diketones such as europium, ytterbium, praseodymium. Okay? And these reagents, they are reversibly bound to the free electrons of the heteroatoms. So the peaks of the other groups in the molecule, depending on the distance from the complex center, they will slide into a low area. Okay, they will slide into a low area with europium and ytterbium complexes, and high area में चले जाएंगे with the praseodymium complex, and so the peaks will be separated. So we have come to the end of the basics of NMR spectra. So we will be starting with mass spectra as well. The instrumentation part for NMR spectra, so we have already discussed basics. Last class may be discussed. So let us take a minute and then we start with mass spectra. So we are starting with mass spectra. So we're going to discuss the basic principles, the theory, the brief outline, instrumentation कैसे होता है, what do you mean by ion formation, what is meant by fragmentation processes, patterns, and how it relates to parent structure and functional groups. Okay, so we'll be finishing this quickly. So mass spectra, as the name itself suggests, it can be used for molecular analysis using the masses. You can use the masses to see the molecular analysis, and it is जैसे कि हम लोग देखे थे इंटरेक्शन ऑफ इलेक्ट्रोमैग्नेटिक रेडिएशन विथ मॉलिक्यूल्स, तो वहां पे क्या हो रहा था, जब रेडिएशन जो जस्ट बीइंग एब्जॉर्ब बाय द मॉलिक्यूल्स, जस्ट बीइंग एब्जॉर्ब बाय द मॉलिक्यूल्स, एंड उसमें वाइब्रेशनल एनर्जी लेवल्स चेंज हो रहे थे, आपके इलेक्ट्रॉनिक एनर्जी लेवल्स चेंज हो रहे थे, बट एसेंशियली उसका केमिकल कॉम्पोजिशन चेंज नहीं हो रहा था. ऐसा कुछ नहीं था कि सैंपल डिस्ट्रॉय हो जाएगा, द सैंपल यूज्ड टू बी इंटैक्ट, बट इन मास स्पेक्ट्रोस्कोपी इट्स अ डिस्ट्रक्टिव इंटरेक्शन. ओके, इट इज अ डिस्ट्रक्टिव इंटरेक्शन. एंड यहाँ पे हम लोग का क्या हो रहा है कि सैंपल को लेके whenever it is being bombarded by high energy particles, whenever it is being bombarded with high energy particles, it is splitting into constituent particles. बहुत सारे constituent particles है, उनके different different masses है, and उन masses को हम लोग analyze करके predict कर सकते हैं कि parent molecule क्या हुआ होगा. So that is the basic principle of mass spectroscopy. It involves the production and separation of ionized molecules and their ionic decomposition product. And finally, the measurement of the relative abundance of different ions can be produced. So it is a destructive technique because the sample is consumed during analysis. आपको sample नहीं मिल सकता after the analysis is completed. So here एक molecular ion होता है, ठीक है. एक पहले इनिशियल स्टार्टिंग फेज में एक मॉलिक्यूलर, पहले मॉलिक्यूल को मॉलिक्यूलर आयन में कन्वर्ट कर दिया जाता है, एंड देन इट प्रोड्यूसेस सम फ्रैगमेंटेड आयंस बाय क्लीवेज ऑफ डिफरेंट बॉन्ड्स. ओके, क्लीवेज होने के बाद वॉट एवर द फ्रैगमेंटेड आयंस आर देयर, दे गिव अ पैटर्न, and that pattern is known as your mass spectrum. And for each compound that is unique, because obviously the fragments that will be found will be different for different compounds, and they can be used as the chemical fingerprint to characterize the sample. So what is the basic principle? As we saw, molecules will be bombarded. First step, molecules will be bombarded with a beam of energetic electrons. Okay, molecules will be bombarded with a beam of energetic electrons. जैसे ही bombardment शुरू हुआ, first the molecules will be ionized and then they will be broken up into many different fragments. Okay, they will be broken up into many fragments, and some of which will be positive ions. Okay, some of which will be positive ions. Now each kind of ion has a particular ratio of mass to charge. Each kind of ion has a particular ratio of mass to charge, that is the m/e ratio will be there. Now, for most ions, the charge is 1. For most ions, the charge is 1. So, m/e ratio is simply the molecular mass of the ion. So, m/e ratio will simply be the molecular mass of the ion. Now, it is used in two general ways. Okay, it is used in two general ways to prove the identity of two compounds. Okay, to prove the identity of two compounds, or to establish the structure of a new compound, or to establish the structure of a new compound. And it helps to establish the structure of a new compound in several different ways. Okay, it helps to establish the structure of a new compound in several different ways and can give you the exact molecular mass. Okay, it can give you the exact molecular mass. It can also give a molecular formula, or it can reveal the presence of certain structural units in the molecule. What is the mass spectrum? हमने कहा था that it is the fragmentation pattern. Okay, but what does it deal with? What is the plot essentially? Plot will be the relative abundance of ions. Okay, relative abundance of ions against the mass to charge ratio. This mass to charge ratio is a very important parameter in your mass spectrum. So it's a plot of relative abundance of ions against the mass to charge ratio. So how is the beam of energetic electrons generated, जिससे हम लोग organic compound को bombard कर रहे हैं, and organic compound here you are essentially converting that into a vapor state first. Okay, you're converting that into a vapor state, and उसको आप beam of energetic electrons के साथ bombard कर रहे हो. Now how are you saying that the electrons will be energetic? Because they are accelerated. Okay, they are accelerated from a filament, and you are giving them a particular energy of 70 electron volts almost to form positively charged ions, or these are known as molecular ions. The additional energy of the electrons then goes into breaking the bonds in the molecular ion. Okay, they break the bonds in the molecular ion, and this undergoes fragmentation, to yield several neutral or positively charged species. Okay, several neutral or positively charged species. This fragmentation may also result in the formation of a even electron ion and radical. And the various positive ions which are formed, they can be accelerated and deflected by magnetic or electric fields. Excuse me. The deflection of ions but depends on the mass, charge, and velocity. And for a given charge, the velocity and deflecting force, the deflection is less for a heavy particle as compared to that of a light one. Okay, as compared to that of a light one, this deflection will be less for a heavy particle. So many kind of beams will be produced, okay, which contain ions with the same m by z values. And these beams, whenever they are striking against a photographic plate, they will not only appear as separate lines, separate distinct sharp lines. जैसे हम लोग को वहां पे peaks मिले थे, and कभी broad मिल रहा है peak, कभी splitting हो रहा है, यहाँ पे single sharp lines आएंगे, only single lines आएंगे. But यहाँ पे intensity बहुत important है. So not only the position, but also the intensity will be very important. So here we are plotting the m by z value against the relative abundance. So the most abundant ion in the spectrum, हम उसको पहले एक relative value दे देते हैं, and that is termed as the base peak. उसको कहा जाता है base peak. So what is the base peak? Base peak is the most abundant ion in the spectrum, which is 100%. उसका assignment है 100%, and we will be plotting the m by z value against the relative abundance. As we have said pehle, what is the difference of mass spectrometer from the usual structure determination method, जैसे कि IR, NMR और UV? पहला कि ऐसा कोई रेडिएशन का एब्जॉर्प्शन नहीं हो रहा है, देयर इज नो एब्जॉर्प्शन ऑफ रेडिएशन. और सेकंड, हम लोग दूसरे में जो भी चेंजेस हो रहे हैं मॉलिक्यूल्स में, दे आर फिजिकल चेंजेस एंड दे आर रिवर्सिबल. Okay, they are reversible physical changes as they deal with the internal motion of the electrons or the energy levels or some kind of motion within the molecule itself or rearrangement within the molecules, which can be easily reversed once the experiment is over. But in mass spectrometer, the compound undergoes irreversible chemical changes, so you cannot get back the sample. Also, these are more drastic than the usual chemical reaction because of the bombardment of energetic electrons. Now this is the instrumentation of a mass spectrometer. Very carefully just see. Okay, principle and instrumentation of mass spectrometer. तो यहाँ पे in the inlet हम लोग पहले जब sample डाल रहे हैं उसको vaporized form में डाल रहे हैं. पहले there might be an additional step here जहाँ पे sample को vaporize किया गया, and we are led to the ionization chamber. Okay, we are led to the ionization chamber. वहाँ पे ionization chamber में we are separating them into molecular ions, base peaks and other fragments, because they are hit by the energetic electrons. They are then accelerated by the electromagnet, and different peaks will be deflected in different directions. Finally, जो fragments होंगे और जितना deflection उनका होगा, you can detect it here, and that detector will be amplifying the signals, and finally you will be getting the chart recorder. Okay, you will be getting the chart recorder. So again we are going to talk about this in detail. So ionization process में क्या होता है? The atom is ionized by knocking one or more electrons off to give a positive ion. Okay, they are always यहाँ पे ions हमेशा positive होंगे. So this is how the ionization chamber is there. Vaporized sample आते ही यहाँ पे एक ion repeller है. There's an electron trap. The electrons will be here, एंड फाइनली जब निकलेगा तो वो पॉजिटिव आयन होके निकलेगा. Okay, here the electrons will be trapped. So the particles in the sample, they are bombarded with a stream of electrons, and जैसे ही bombard हुआ sample में से एक दो इलेक्ट्रॉन निकल गए. Okay, इलेक्ट्रॉन निकल गए. So it is a electron in electron out process. Okay, remember this is an electron in electron out. जैसे इलेक्ट्रॉन उसके ऊपर आया, वो एक इलेक्ट्रॉन सैंपल से निकाल दिया. So we got the positive ions. Now the positive ions usually carry a charge of +1, एंड फाइनली आयन जो चेम्बर है वहां से वो निकल जाते हैं. ओके, ये निकल जाते हैं एंड आयन रिपेलर से, that is also another metal plate which is has a positive charge, that is known as ion repeller, क्योंकि इसका भी पॉजिटिव चार्ज है, उसका भी पॉजिटिव चार्ज है, तो वहां से वो निकल जाएगा. Now how are these accelerated? How are these accelerated? हम लोग ionization chamber से निकल रहे हैं, but at the same time the acceleration is also take place. So the ions which are coming out will have the same kinetic energy. Okay, they will have the same kinetic energy. They are repelled away from the ionization chamber and then they pass through 3 slits with voltage in the decreasing order. The middle slit carries some intermediate voltage and the final will have at 0 volts, and all the ions will be accelerated into a finely focused beam. Now the ions are then deflected by a magnetic field. Okay, ions are deflected by a magnetic field according to the masses. जितना लाइट होगा उनका डिफ्लेक्शन उतना ही ज्यादा होगा. Okay, जितना लाइट होगा उनका डिफ्लेक्शन उतना ही ज्यादा होगा. And it also depends on the number of positive charges on the ion. Okay, it also depends on the number of positive charges on the ion. So जितना ion charge होगा उसका deflection उतना ज्यादा होगा. So amount of deflection is dependent on 2 factors. One on how light they are, and another on how much charge there is. Okay, how much charge there is there. So you can see हम लोग जो डायग्राम किए थे यहाँ पे मिक्स्ड आयन स्ट्रीम आया एंड by the electromagnets they were deflected. तो यहाँ पे 3 streams you can see, ion stream A, B and C. Just take down this diagram. Okay, so as we have said, the amount of deflection depends on the mass of the ion. So lighter ions are deflected more and the charge on the ion. So with 2 or more positive charges, they are deflected more than ones with only 1 positive charge. So how are they detected? How are the beam of ions passing through the machine detected? So ion stream B आया. Okay, they make it right through the machine to the ion detector. दूसरा ions, they're also colliding with the walls here. Okay, and they are picking up electrons. Again, they are getting neutralized, and then finally they are removed from the mass spectrometer by the vacuum pump. So when an ion hits the metal box, उसका charge neutralized हो रहा है because the electron is jumping from the metal onto the ion. And finally, that leaves a space amongst the electrons. So they are all shuffling along to fill it. Okay, they are all shuffling along to fill it. And the flow of electrons finally is detected as an electric current. And that current is amplified and recorded. So जितना ions आएंगे उतना current ज़्यादा होता रहेगा. Now, what is the fragmentation process? We have talked a lot about the fragmentation process. So what does that occur? So bombardment जितना होगा, and the energy will be 10 to 15 electron volt. They will result in ionization by removal of 1 electron, and that will lead to the molecular ion formation. And when the energy is increased even more to 50 to 70 electron volt, the molecular ions will also acquire a high excitation process, and they will be breaking down into various fragments. And this is known as fragmentation process. So what kind of ions can we expect in a mass spectra? What kind of ions we can expect in a mass spectra? So you can expect the parent ion or the molecular ion. Okay, you can expect the parent ion or the molecular ion. You can expect a fragment ion. Okay, you can also expect some kinds of ions that are generated by rearrangement, and also multi-charged ions, negative ions, and metastable ions. So these are kind of the 6 types of ions that you can expect during mass spectrometer. Okay, you can expect these kind of ions during mass spectrometry. So you can just take down these six types of ions. Okay, you can just take down this six types of ions. So the first kind of ion is molecular ion. Now molecular ion को हम लोग कैसे डिनोट करेंगे? So पहला molecular, ये molecule है, इसमें it is uncharged. When it is bombarded with an electron, क्या होता है? एक molecular ion form होता है and दो electron निकल जाते हैं. So this is one that is bombarded and the other that is gone from the sample. Okay, that is becoming lost from the sample. So the order of energy that is required to remove an electron is as follows. अगर सिग्मा इलेक्ट्रॉन्स है, सबसे ज्यादा उसको इशू होगा निकलने में. ठीक है, सिग्मा इलेक्ट्रॉन सबसे ज्यादा प्रॉब्लम करेंगे निकलने में, इसलिए एनर्जी भी उसको ज्यादा चाहिए. नॉन कॉन्जुगेटेड पाई इलेक्ट्रॉन्स will also take more amount of energy than conjugated pi electrons, and सबसे कम एनर्जी क्या लेगा? तो नॉन बॉन्डिंग एंड लोन pair of electrons, because they are loosely bound. Okay, because they are loosely bound, they will take less amount of energy to come out. And also these kind of molecular ions, they will disintegrate within 10 to power of minus 10 to 10 to power of minus 13 seconds, and they will give a positively charged fragment and a radical in the simplest case. So यहाँ पे stability of molecular ion का order दे दिया है. So aromatic peaks are the most stables. Okay, aromatic peaks are the most stables, and for least will be the alcohols. Least will be the alcohols. What is the characteristic of a molecular ion? Molecular peak तभी observe किया जाता है if the molecular ion is stable. Okay, if it remains intact enough, if it is not itself getting fragmented. So this peak will give the molecular weight of the compound. Okay, they will give the molecular weight of the compound. So this will be the peak of the higher mass number. सबसे highest mass number का जो peak होगा, that will be your molecular ion peak. Okay, so this is a very important parameter in the identification of the compound. For example, अगर इथेन हम लोग ले रहे हैं, ओके, इथेन का इफ यू आर गेटिंग अ फ्रैगमेंट एट C2H5 प्लस, एंड अगर पीक हमको मिला है मास टू चार्ज रेशियो ऑफ 29 में, मतलब ये इथेन का है. ओके, दिस विल बी द इथेन. सो द मास टू चार्ज रेशियो ऑफ द मॉलिक्यूलर आयन इज एक्चुअली द मॉलिक्यूलर वेट ऑफ द कंपाउंड. Now whenever more energy is given to the molecular ion, cleavage takes place. Okay, cleavage takes place. तो हमारा जो सपोज हम लोग एथेनॉल लिए हैं, ठीक है, एथेनॉल लिए हैं, उसका मॉलिक्यूलर आयन पीक है CH3OH प्लस. ठीक है, प्लस डॉट मतलब एक इलेक्ट्रॉन जा चुका है. तो CH3OH उसका मास पर चार्ज रेशियो क्या है? 32. अगर उसको फ्रैगमेंट में कर दूं, एक H यहां से निकाल दूं, तो क्या हो जाएगा? CH2OH प्लस, जिसका मास पर चार्ज रेशियो है 31. सो दैट इज ऑल्सो क्लीवेज, क्योंकि एक CH बॉन्ड का क्लीवेज हो गया. ठीक है, एक CH बॉन्ड का क्लीवेज हो गया, एक हाइड्रोजन निकल गया, तो जो मॉलिक्यूलर आयन उससे प्रोड्यूस्ड हुआ उसका भी मास पर चार्ज रेशियो रिकॉर्ड हो जाता है. एंड दैट इज ऑल्सो अ कैरेक्टरिस्टिक ऑफ द मॉलिक्यूलर स्ट्रक्चर, कि इसके क्लीवेज की वजह से शायद ये मास टू चार्ज रेशियो में एक मॉलिक्यूलर आयन प्रोड्यूस हुआ है. Now rearrangement ions, the rearrangement ions are the fragments. Okay, they are the fragments जिनके origins you cannot describe by simple cleavage of bonds in the parent ion, but they are the result of intramolecular atomic rearrangement during fragmentation. They are the result of intramolecular atomic rearrangement during fragmentation, and they are due to recombination of fragment ions, and they are known as rearrangement peaks. They are known as rearrangement peaks. So for example, if you are taking diethyl ether, okay, diethyl ether if you are taking, and you have a prominent peak which occurs at mass per charge ratio of 31, this is due to the ion CH3O plus. Okay, जो rearrangement हुआ है C2H5O plus ions के साथ, उनका rearrangement होके you are getting the ion CH3O plus. Now you can also get some multi-charged ions. Now we have been talking about M plus, but ऐसा भी हो सकता है कि some ions can exist with 2 or 3 charges. जैसे ये single charge हम लोग देख रहे थे, but they can also exist as doubly or triply charged ions. So M plus plus भी हो सकता है, M2 plus भी हो. A single charge is the normal operating conditions. बट डबली ट्रिपली चार्ज भी रिकॉर्ड होते हैं, बट द मास बाय चार्ज वैल्यू जो होता है सिंगल चार्ज का, उसका हाफ या वन थर्ड में वो रिकॉर्डेड होगा. यूजली दे आर वेरी कॉमन इन इनऑर्गेनिक मास स्पेक्ट्रम पर्टिकुलरली, क्योंकि द गैसेस लाइक कार्बन मोनोक्साइड, N2, कार्बन डाइऑक्साइड, ऑक्सीजन, उनका पीक्स आपको मिल जाएगा वही +2 के +2 में मिल जाएगा. सो CO+2, N+2, O+2 दे आर वेरी कॉमन. So these are more common in heteroaromatic compounds. Formation of the multiple charge ions is more common in heteroaromatic compounds. Now let's talk about negative ions. कुछ चीजें negative ions भी हो सकते हैं. हम लोग we have talked about mostly positive ions, but they are very rare. Okay, negative ions are very very rare, and they are also not very useful in structural determinations. ठीक है, they are not very useful in structural determinations. We are mostly concerned with positive ions at this point. Now what happens about metastability? Okay, what happens about metastability? So if you have a parent ion and you have a fragment, they can give rise to a new ion, that is a daughter, plus a neutral molecule or a radical. Okay, they can also have a different kind of product, that is a neutral molecule or a radical. So M1 plus will be giving rise to a new ion, that is M2 plus. But this kind of situation can also happen when it is being accelerated. Okay, they can also fragment when it is being accelerated itself. It can decompose to M2 plus. So the resultant जो भी होगा M2 plus जो होगा, it will not be recorded either at M1 और M2. अगर acceleration के वक्त उसका decomposition हो गया तो ना वो M1 के पोजीशन में आएगा ना M2 के पोजीशन में आएगा, but it will come at a position M star. Okay, it will come as a position M star, and उसका focusing ठीक नहीं होगा, and वो peak, instead of a single sharp line, it will give us a broad peak. ठीक है, it will have a broad peak, and जब भी हम लोग ऐसे broad peaks देखते हैं, we can say that this ion is a metastable ion. Okay, this ion is a metastable ion. So ion source से जब डिटेक्टर की तरफ जा रहा है, अगर यहाँ पे ही एक्सेलरेशन के टाइम पे उसका आयन फॉर्मेशन हो गया या फ्रेगमेंटेशन हो गया, then you will get the M star peaks, and these M star peaks are not fully focused and they are very broad. Also, they have lower kinetic energy than normal ions, so the peaks will also be smaller than the M1 and M2 peaks. So हम लोग को 3 characteristics यहीं पे मिल गए. They will be broader, they will have smaller peaks, and they will also not be too sharp. Okay, they will not be too sharp. And why do they occur? They arise from the fragmentation that takes place during the flight down through the ion rather than in the ionization chamber. So molecular ions क्या करते हैं in the ionization chamber? एक, either they will decompose completely. ठीक है, they will be decomposing completely. So molecular ion peak कभी कभार दिखता नहीं है. They never reach the collector. Okay, they never reach the collector. या फिर they will survive long enough to reach the collector और उसका लाइफ टाइम वहां पे recorded हो जाएगा. But how do these metastable ions, in case they're there, how do they establish the structure? Because they are used to distinguish between the different fragmentation processes. तो कैसे fragmentation हुआ और कैसे fragmentation होता है molecule में, you can find out through the metastable ion peaks. Now, how do these fragmentations occur? Do they occur randomly? Okay, एक होता है relative height of the molecular ion peak. This is greatest for a straight chain compound. Okay, this is greatest for the straight chain compound, and it decreases as the degree of branching is increasing. Okay, it is decreasing as the degree of branching is increasing. The relative height of the molecular ion peak also decreases with increasing molecular weight. Okay, जितना molecular weight increase किया, उसका height of the molecular ion peak will also decrease, and this is particularly for a homologous series. This is also particularly for a homologous series. You can see that the cleavage is favored at alkyl substituted carbon atoms. जितना substitution है उतना cleavage possible है. Now you can also draw parallels between the SN1 and SN2 reactions. जैसे 3 डिग्री में हुआ, ओके 3 डिग्री कार्बन में जब वो कार्बोकेटाइन फॉर्मेशन होता है तो उसका 3 डिग्री सब्स्टिट्यूशन, जितना सब्स्टिट्यूशन होगा उसका 3 कार्बोकेटाइन फॉर्मेशन इज मोर फेवर्ड एंड इट विल बी मोर स्टेबल एज वेल. सो हियर ऑल्सो सेम लॉजिक अप्लाइज, जितना एल्किल सब्स्टिट्यूशन होगा उसका क्लीवेज उतना लाइकली होगा. So because this is of the increased stability of a tertiary carbon atom over a secondary, which is again more stable than a primary. Now what is the Stephenson's rule? What is the Stephenson's rule? When an ion fragments, the positive charge remains on the fragment of the lowest ionization potential. Okay, positive charge will remain on the fragment of the lowest ionization potential. The largest substitution at a branch, वो पहले एक रेडिकल में पहले चला जाता है, ठीक है. Because the long chain radical, it can achieve some stability by delocalization of the lone electron. For example, if we are having a cleavage of a 1-methyl pentane, उसका largest fragment जो है वो पहले चला जाएगा. And in the fragmentation, the positive charge will remain on the more high substitution fragments, that is the one with lower ionization potential. So if you have double bonds, if you have cyclic structures, if you are heteroaromatic rings and aromatic rings, they stabilize the molecular ion a lot. Okay, they stabilize the molecular ion a lot and they increase the probability of its appearance. Okay, they increase the probability of its appearance. Now these double bonds, they also favor allylic cleavage. These double bonds, they also favor allylic cleavage and give the resonance stabilized allylic carbonium ions. Okay, so mass spectrum of 1 butene अगर हम लोग देखें, this is 1 butene. So अगर मैं यहाँ से एक क्लीवेज करके लेके चली जाऊं, ठीक है, अगर मैं ये -CH3 लेके चली जाऊं, then we will get what? CH2 double bond CH, CH2 plus है, ठीक है. Now this can also go rearrangement, this can also go rearrangement. ये CH2 plus इस तरफ भी ट्रांसफर हो सकता है. Okay, though this will be a resonance stabilized structure. This will be a resonance stabilized structure. Similarly, saturated rings अगर है तो alkyl side chains if they are there, तो cleavage पहले वहां पे हो जाएगा. Okay, and जो positive charge होगा वो ring fragment के पास होगा. Okay, ring fragment के पास होगा and जैसे ring fragment के पास होता है वहां पे एक rearrangement we will also see in the subsequent slides कि वो rearrangement होके and एक alkene subtract होके you can get another particular rearranged peaks. Okay, you can get a particular rearranged peak. Alkyl substituted aromatic compounds में भी rules है. So cleavage सबसे ज्यादा होता है जो बीटा अगर अल्फा बीटा है तो बीटा में ये वाला सब्स्टिट्यूशन पहले होता है, ठीक है. दिस वन विल गिव, सो बेंजिल आयन हो जाएगा. बेंजिल आयन होते ही उसको एक रीअरेंजमेंट होता है विच इज नोन एज द मर्क-लैफर्टी रीअरेंजमेंट आयन. मर्क-लैफर्टी रीअरेंजमेंट आयन, जैसे ही ये बेंजिल आयन का हमको मिला वैसे ही वी विल बी गेटिंग अ ट्रोपिलियम आयन, ठीक है. अ ट्रोपिलियम आयन MZ91. MZ91 जैसे ही दिखा मतलब there was some substitution which got cleavaged out and एक मर्क-लैफर्टी रीअरेंजमेंट हुआ. So from MZ92 we got MZ91. So this is a characteristic feature of a mass spectrum कि अगर हम लोग 92 और 91 में पीक्स मिल रहा है मतलब बेंजिल आयन है, which means कि कोई सब्स्टिट्यूशन था बेंजीन रिंग में एंड वो अभी रीअरेंजमेंट होके ट्रोपिलियम आयन फॉर्म कर चुका है. ऑल्सो क्लीवेज हम लोग पहले जब देखेंगे, पहले जितने स्मॉल मॉलिक्यूल्स हो सकते हैं पहले उनको निकाल देंगे. जैसे अगर वाटर मॉलिक्यूल पॉसिबल है उसको निकाल देंगे, अमोनिया, हाइड्रोजन सल्फाइड, कार्बन मोनोऑक्साइड, इवन मिथाइल ग्रुप्स, मर्कैप्टन्स, कीटोन्स, अगर अल्कोहलिक ग्रुप है वो पहले निकाल देंगे. सो पहले छोटे छोटे ग्रुप्स को हम लोग निकाल के उसका देखेंगे कि M/Z रेशियो का जो पीक है वो है कि नहीं. ओके, एंड देन वी विल गो फॉर द रीअरेंजमेंट. Now, what kind of factors can influence the fragmentation process? You can have bombardment energies, functional groups, and thermal decomposition. You can have bombardment energies, functional groups, and thermal decomposition. So general modes of fragmentation what will be there? एक होता है homolytic cleavage. ठीक है, homolytic cleavage you have seen in photochemical processes. We have all learnt about homolytic cleavage in photochemical processes. And similarly, you can also have heterolytic cleavage where the two parts will not be equal. They will not be equal. And you can also have retrodialyl reactions. Rearrangement reactions, Amisha, they are accompanied by transfer of atoms. We have seen one example of Merck-Lafferty rearrangement, जहाँ पे the benzyl ion got rearranged into a tropylium ion. Okay, so there was a distinct rearrangement followed by also elimination, and you can also have scrambling. So this is an example of homolytic cleavage. So यहाँ पे ये वाला bond, okay, this particular bond that got cleavaged out, and you are left with two types of fragments where you're getting one positively charged fragment and one neutral molecule. Okay, here this is due to the homolytic cleavage. What it ensures that the fragmentation is due to electron redistribution between bonds. So this is due to electron redistribution between bonds. Similarly, heterolytic cleavage is there. The fragmentation is by movement of two electrons. Okay, so both the electrons of the bond will be taken over by one of the atoms, and the fragments will be having an even electron cation and a radical with the positive charge that will be residing on the alkyl group. So जैसे conventional arrow systems होते हैं कि there's a transfer of a pair of electron, वैसे ही we will be doing the heterolytic cleavage. So if you have a ROR, तो यहाँ पे इस तरफ इसका transfer हो जाएगा. So he will get a molecular charged ion here and a neutral molecule here. Similarly, if you have a Br, ठीक है, ब्रोमीन अटैच है तो ब्रोमीन हम निकाल के ब्रोमीन न्यूट्रल की तरह निकल जाएगा या रेडिकल की तरह निकल जाएगा, and C4H9 will be the peak that we observe in the mass spectrum. Similarly, if you have a retrodialyl reaction, this will be elimination by multiple sigma bond ruptures. So जैसे कि cyclohexene, they can break down into diene and dienophile. Okay, they can break into diene and dienophile. So ऐसे structures they will be recorded in the mass spectrum. So these kind of structures will also be recorded in the mass spectrum. Now, rearrangement reactions can also be accompanied by transfer of atoms. For example, scrambling. Fragmentation can give rise to a stable carbocation. So they can take place at a bond which will give a stable carbocation. The molecular ion from the alkyl benzene, they will undergo fragmentation with the benzylic bond, and the final product will be a 7-membered cyclic ion known as tropylium ion. Merck-Lafferty rearrangement mein, there is fragmentation due to rearrangement of the molecular or parent ion. So there will be an intramolecular atomic rearrangement. Okay, there will be intramolecular atomic rearrangement. And when fragments are accompanied by bond formation or bond breaking, the rearrangement process will said to have occurred. Okay, the rearrangement will involve the transfer of hydrogen from one part of the molecular ion to another, and we will get a 6-membered cyclic transition state. Because and this process will also be favored energetically because जितने bonds breaking हो रहे हैं उतने bonds formation भी हो रहे हैं. Okay, bond breaking will be equal to bond formation. So as we have seen in the Merck-Lafferty rearrangement of benzyl ion, so we are seeing that this process is favored energetically. And gamma to the carbonyl group, अगर है कोई compounds, okay, if you have compounds containing hydrogen atom at a position gamma to the carbonyl group, they can have a relatively intense peak. So this is another example of a Merck-Lafferty rearrangement. So suppose we have this kind of an arrangement and you have a carbonyl group. Carbonyl group में अगर alpha, beta, gamma, ठीक है, अगर यहाँ पे एक hydrogen atom है, तो this can get involved in the rearrangement process. ये bond जाके यहाँ पे आ सकता है. The double bond of the C double bond O can break, and again this rearrangement can happen. So we will get a neutral olefin molecule and an enol. Okay, we can have a enol. So this kind of rearrangement is also possible. So because this hydrogen atom is abstracted by the carbonyl oxygen. Okay, this is abstracted by the hydrogen atom, and उसका structure ही ऐसे हो सकता है कि it will undergo the rearrangement very easily. So common Merck-Lafferty peaks, you should be well versed in how and what kind of Merck-Lafferty peaks can happen in carbonyl groups. अगर एल्डिहाइड है एंड यू आर गेटिंग अ पीक एट 44, आपको इमीडिएटली सोचना है कि ये मैक-लैफर्टी की वजह से है. सिमिलरली मिथाइल कीटोन का 58 पे आता है. इफ यू हैव एन अमाइड यू कैन गेट अ मैक-लैफर्टी पीक एट 59. ठीक है. So these are the common kinds of Merck-Lafferty peaks which you can find in the spectra of carbonyl group. Similarly, another fragmentation can obviously occur. This is the most common elimination. ठीक है. छोटे छोटे molecules we have already discussed what kind of small molecules are there. If you can lose water molecules, you can lose carbon dioxide, carbon monoxide, okay, and you can lose them from the molecular ion during fragmentation. The alcohol readily loses water molecules and shows a peak of 18 mass units less than the peak of molecular ion. So agar we have an alcohol and we are getting a peak at 18, okay, if you're getting a peak at 18, then you should know that the water molecule came out of the alcohol. Okay, water molecule came out of the alcohol. अगर हमारा alkane branched hai, if you have a branched alkane, the bond fission can take place adjacent to the branching point. Okay, they can take place adjacent to the branching point. So this leads to formation of more stable carbocations. For example, 3-methyl pentane. Okay, you can get a 3-methyl pentane. तो एक हम लोग का MBZ at 57 मिल गया. For MBZ 86, you can clearly see कि यहाँ से ये particular bond rupture हुआ है. So this particular branch is coming out as a peak at MBZ 57. Now you can have different fragmentation patterns and fragmentation, and this will be characteristic to the parent structure. So अगर हम लोग कोई भी मास स्पेक्ट्रा देख रहे हैं, कुछ उसके फीचर से हमको पता चल जाएगा कि वो एल्केन्स का है या एल्कीन्स का है या एरोमेटिक रिंग्स का है, वो हमको पता चल जाएगा. There are certain features that you can watch out for. For example, for straight chain compounds, ठीक है, अगर if you are seeing an alkane mass spectra, the first molecular ion peak present होता है. ठीक है, बहुत सारे स्पेक्ट्रम में एब्सेंट रहता है, बट फॉर एल्केन्स पर्टिकुलरली मॉलिक्यूलर आयन पीक वीक भी है तो प्रेजेंट रहेगा. Relative height of the parent peak will decrease as the molecular mass increases in the homologous series. Also, देखना है कि जितने भी peaks हैं, they can consist of peaks will be separated by 14 mass units. अगर ऐसे एक स्ट्रेट चेन एल्केन है और एक एक CH2 ग्रुप का क्लीवेज होते जा रहा है, तो अगर 14 के डिफरेंस में डिफरेंट आयंस प्रोड्यूस्ड हो रहे हैं तो वो एल्केन है. लार्जेस्ट पीक जो होगा वो CnH2n+1 फ्रैगमेंट होगा, उसके बाद CnH2n होगा, CnH2n-1 होगा. तो एक एक हाइड्रोजन भी जब क्लीवेज होके निकल रहा है उसको भी नोट करना है. तो लार्जेस्ट पीक एक होगा, एक हाइड्रोजन के लॉस पे और एक पीक होगा, 2 हाइड्रोजन के लॉस पे और एक पीक होगा. ऐसे भी पीक्स होते हैं जो CH2 के लॉस पे होंगे, तो यू हैव टू वॉच आउट फॉर दिस. अगर CH2 के पीक्स पे बहुत सारे क्लस्टरिंग पीक्स हो रहे हैं, देन दैट इज योर एल्केन. सिमिलरली ब्रांच्ड अगर है तो मॉलिक्यूलर आयन का अपीयरेंस कम हो जाता है, और अगर भी आता है तो इट विल बी वेरी वीक, एंड bond cleavage takes place at the site of branching. So जैसे ऐसे cleavage होंगे, there will be more stable secondary or tertiary carbonium ions, and the largest substitute at a branch that will be eliminated readily as a radical. The radical also achieves stability by the delocalization of lone electrons. The greater number of fragments will result from the branch chain compound compared to the straight compound, and this will be due to greater pathways available for cleavage. So alkenes में क्या खासियत है? The molecular ion containing one double bond, they will tend to go allylic cleavage and they will give a resonance structure. So the molecular ion peak will be more intense than the saturated analogs अगर unsaturated compounds में वो पाए गए. ठीक है, molecular ion peak will be more intense than the saturated analog, that is alkenes से alkene का better रहेगा, because after the removal of one of the pi electrons उसका resonance stabilization ज्यादा होता है. Okay, उसका resonance stabilization ज्यादा होता है. It also again shows group of peaks which are 14 mass units apart, and यहाँ पे भी Merck-Lafferty rearrangement is more active. तो इफ यू हैव एन एल्कीन लाइक दिस, ओके, इफ यू हैव एन एल्कीन लाइक दिस, ये जो हाइड्रोजन है ये निकल गया, दिस हाइड्रोजन बॉन्ड कम्स, so this double bond comes here, again this gets rearranged, so we can get a Merck-Lafferty peak at 42 for one pentene. So you always have to consider the possibility कि जो पीक आया है जो किसी से मैच नहीं कर रहा है, अगर देख रहे हो कि कोई भी मास यूनिट के लॉस से ये मैच नहीं कर रहा है, जैसे कि वाटर के निकलने से, हाइड्रोजन के निकलने से, CH2 के निकलने से, कोई दूसरा स्मॉल मॉलिक्यूल के निकलने से जो मास होना चाहिए वो मास नहीं है, which means it is a rearranged peak. Okay, it is a rearranged Merck-Lafferty rearrangement हुआ है. Similarly, you have to see कि whether there can be any retro-Diels-Alder reaction or not. Retro-Diels-Alder की वजह से हमको कोई पीक मिल रहा है कि नहीं. एरोमेटिक कंपाउंड्स का स्पेशलिटी ये है कि मॉलिक्यूलर आयन पीक प्रोमिनेंट होता है, ऑल्सो M+1 और M+2 होगा ही, ठीक है, M+1 और M+2 होगा ही. ऑल्सो एरोमेटिक कंपाउंड में हमको Merck-Lafferty का पीक देखना होता है, ट्रोपिलियम कटायन का 91 है कि नहीं, और अगर ट्रोपिलियम कटायन का 91 है, ट्रोपिलियम कटायन से हमको एक पीक मिल जाता है 65 पे, वेयर इट इज एलिमिनेटिंग अ neutral acetylene molecule. Okay, it is eliminating a neutral acetylene molecule, so you have to be also careful. M+1 M+2 देखना है, Merck-Lafferty का देखना है 91 पे आ रहा है कि नहीं और एक 65 पे आ रहा है कि नहीं, क्योंकि एक acetylene molecule भी eliminate हो रहा है. So that is how you detect aromatic compounds. Okay, similarly for alcohols, 3 डिग्री अल्कोहल्स में तो मॉलिक्यूलर आयन पीक दिखेगा ही नहीं, अगर 1 डिग्री 2 डिग्री में भी दिख रहा है तो एविडेंस ज्यादा नहीं होता है. ऑल्सो फ्रेगमेंटेशन जो होता है वो अल्फा क्लीवेज होता है, जो ऑक्सीजन एटम के जो सीसी बॉन्ड है एडजेसेंट टू जस्ट द ऑक्सीजन एटम, दैट विल अंडरगो फ्रेगमेंटेशन एंड दैट विल बी द अल्फा क्लीवेज. सो 1 डिग्री अल्कोहल अगर है, इट विल शो पीक्स एट M-18 पीक्स, क्योंकि वाटर का लॉस हो गया. सो H2O जैसे ही निकल गया, M-18 पीक्स निकलने लगेंगे. अगर अल्कोहल का चेन लॉन्ग है, सो इट विल शो पीक्स कॉरेस्पॉन्डिंग टू सक्सेसिव लॉस ऑफ H रेडिकल्स. तो आपको M-18 पीक्स अगर दिख रहे हैं प्लस M-1, M-2, M-3 ऐसे करके H radicals are going away, then you can be sure that this is an alcohol. Also CH2 double bond OH, this is the most significant peak in the spectra of 1 degree alcohols, so be very careful about the mass of this. If you are taking now the mass of this and you see this peak in spectra, then you can be sure that 1 degree alcohol है, and just check कि M-1, M-2 ऐसे करके सक्सेसिव पीक्स है कि नहीं और M-18 के कोई पीक्स है कि नहीं. सिमिलरली एरोमेटिक अल्कोहल में वही सारी चीजें देखनी है जो एरोमेटिक और अल्कोहल्स में देखना है. सो पेरेंट आयन का एविडेंस ज्यादा होगा एंड बेंजिल अल्कोहल का फ्रेगमेंटेशन 1, 2 और 3 हाइड्रोजन एटम्स का फ्रेगमेंटेशन होगा. ओके, फेनॉल्स में अगेन मॉलिक्यूलर आयन पीक इज इंटेंस and carbon monoxide can be lost. Okay, one important clue as to whether it's a phenol or not is that एक कार्बन मोनोक्साइड का भी लॉस होता है. फॉर एल्डिहाइड्स एंड कीटोन्स कैसे हम लोग फाइंड आउट करेंगे, अल्फा हाइड्रोजन के लॉसेस होते हैं, ठीक है, बीटा क्लीवेज होता है, ऑल्सो CH2 CHO जहां पे भी एन ग्रुप आएगा उसका एक M-43 पीक्स आता है. ओके, M-43 पीक्स कैन come in an aldehyde mass spectra. Ketones के लिए Merck-Lafferty rearrangement is very important, so you have to see whether any cleavages are present due to Merck-Lafferty rearrangement. Similarly for nitro groups, NO2 का जो मास है वो निकाल के हमको देखना है कि ऐसे कोई fragments है कि नहीं which is giving because of loss of NO2. For aliphatic acids, you can see that the carboxyl group can be directly eliminated. The signal will be formed at M/E45, ठीक है, and Merck-Lafferty rearrangement ion can be formed at M/E60, and it is the base peak. In short chain acids, MOH and MCOH peaks are prominent. For halogen compounds, you can see that the compound with one chlorine atom gives a M+2 peak, and it will be 1/3 the intensity of the molecular ion peak. Okay, if you have a bromo derivative, okay, if you have a bromo derivative, then the M+2 peak will be of equal intensity to the molecular ion. So if you are seeing a molecular ion peak and you are seeing just after that you have a m plus 2 peak, then that will be of equal intensity, and you can be sure that it is having a bromo derivative. Similarly, aliphatic chlorine compounds, they will be fragmenting by loss of HCl. Okay, HCl ke loss mein you will get peaks, and they will be peaks at m minus 36, m minus 38, and you'll also get some peaks at 36 and 38. And the abundance of the molecular ion will be decreasing with increase in chain length and increase in branching. Ethers जो होते हैं, they can be cleaved by alpha cleavage and beta cleavage. Please mute yourself.
मतलब मैम को सुनाई नहीं दे रहा है। हेलो।
Hello? Hello?
हेलो।
Am I audible? Hello? Am I audible?
Yes, ma'am, audible. Josh, we have some
हेलो मैम, डोंट
problem.
डिस्टर्ब।
Hello? Am I audible?
Yes, ma'am, you are
हेलो।
audible. Josh, please check you have some problem.
Okay. Thank you for confirmation. So ethers will undergo facile fragmentation. ठीक है, यूजली ethers में बहुत ही वीक molecular ion peak होता है, because जो भी ion उससे fragment होगा that will be highly stabilized by resonance. So molecular ion peak का stability बहुत कम होगा. So the major fragmentation modes, they will occur through alpha and beta cleavages. Because alpha cleavage कब होता है, then the cleavage of a bond alpha to the oxygen will occur. So positive charge कहाँ पे रहेगा, कार्बन पे रहेगा instead of the oxygen. Similarly beta cleavage कब होगा, when it will favor the loss of a larger group. Radical के हिसाब से larger group eliminate हो जाएगा, and then the ion that is resulting, it will undergo further fragmentation to give a series of ions. Similarly, aromatic ethers, molecular ion peak of an aromatic ether is prominent. Primary cleavage occurs at the bond beta to the ring, and the first formed ions, they can again decompose further. So this is a bird's eye view of mass spectrometer. Okay, mass spectrometry, and what kinds of examples are there, what kinds of features of the mass spectra are there. I'm going to give the link to this particular presentation. Okay, you can just download it from this link and go through it quickly. We'll take a 5 to 10 minute break, when where we will just ponder over whatever we have learned till now. I will also be sharing some links जहां से आप लोग practice कर सकते हैं NMR और mass spectra, and you can look at some actual spectra and you can see कि कैसे स्ट्रक्चर डिटर्मिनेशन होता है. एंड आई वुड सजेस्ट कि आप लोग IR, UV और NMR को कंबाइन करके प्रॉब्लम्स जो आते हैं, दोज ऑल्सो यू प्रैक्टिस. आई विल ऑल्सो बी गिविंग सम रेफरेंसेस जहां से आप लोग प्रैक्टिस कर सकते हैं. ठीक है, सो लेट अस टेक अ 5 to 10 minute ब्रेक. आई विल बी शेयरिंग द लिंक्स वन बाय वन, एंड आप लोग वहां से देख लो कि आप लोग क्या क्या प्रैक्टिस कर सकते हैं. सो जस्ट कॉपी एंड पेस्ट ऑन टू अ वर्ड डॉक्यूमेंट. We'll be coming back to discuss a little bit about fluorescence and phosphorescence. Okay, fluorimetry and phosphorimetry. So we'll be discussing that next. So let's take a break. So I hope you have gone through the links. Just copy and paste them onto a Word document. Okay. So you can practice. Some of them are websites where you can find many spectra, and they will allow you to practice through an interactive interface as well. I've also given some links where you can combine UV, IR, and NMR, and then use the knowledge of all three to find out the structure of the molecule. So you have that in your portion where you are going to use these to find out the structure. So for your portion, for your course, it will be very simplistic problems. So essentially, for IR, some peaks will be given, peak positions will be given. For UV also, some peak positions will be given, and for NMR, the notation that I told you, like Q2H, like two proton quartet, one proton triplets, those kind of notations will be given, and you will be asked to find out the molecular structure. So very simplistic problems will be given at your course examinations. Okay. So now let us discuss some concepts relating to fluorescence and phosphorescence. So just wait. So we know some of the basic concepts already, but still we'll be discussing them quickly. So fluorescence is the emission of visible light by a substance which has absorbed light of a different wavelength, and so the emitted photon has a longer wavelength. And phosphorescence is essentially delayed fluorescence. Okay, it is related to fluorescence because it also emits the photon, but the phosphorescent material, it does not immediately re-emit the radiation. There is a time lag, and we will come to know why there is a time lag. And when we are combining these two kinds of emissions, because the excitation of the molecule is due to the absorption of a photon, that is light energy, these kinds of luminescence, they're also known as photoluminescence. So fluorimetry and phosphometry, they are dependent on the phenomenon of photoluminescence. Now, another kind of luminescence is also chemiluminescence, because this is due to radiation emission due to a chemical reaction. So here, electromagnetic radiation is not observed, but it is not absorbed, but it will happen in a chemical reaction. So the oxidation happens because of a chemical reaction. This is an example of how luminol can undergo oxidation under a sodium chlorate conditions to given amino phthalate ion, and this in turn will be a luminescent molecule. Okay, this will in turn be a luminescent molecule. Now, how the fluorescence and phosphorescence happens to occur depends on the Jablonski diagram. Okay, it depends on the Jablonski diagram. So you have several ground states and excited states. Okay, you have the ground state. For example, here you can see that the ground state is S0. Okay, and there are various levels in the ground state as well. Okay, various levels are also occurring in the ground state, and you have a singlet excited state and a triplet excited state. So the singlet excited states are denoted by S1 and S2, and the triplet excited states by T1. And here you are saying that the triplet and the single excited state, they are different. Okay, they are quite different, and usually the crossing between the singlet and the triplet excited state, they are forbidden. Usually जो same spin state के states होते हैं, within them you can have crossing, you can have the crossing. But if you're changing from a singlet to a triplet excited state, that is usually a forbidden transition, and thereby they are occurring very slowly. Okay, they are occurring very slowly. So suppose something is present here in the ground state and it is getting excited to either the singlet or the first singlet excited state or the second excited state, and within these excited states also there will be so many other levels. Okay, there will be so many internal levels. So maybe it is getting excited to the highest singlet excited state, okay, and then gradually they are decaying back to the lowest excited state. After it reaches this particular point, it is getting decayed to the S1. From S2 to S1, one kind of transition is occurring, which is known as the internal conversion. Okay, it is known as the internal conversion. Now, from S1 also, once it relaxes back to the lowest excited state, from the highest excited state to the lowest excited state, once it gets, after that, whatever it is emitting radiation, that is known as fluorescence. The drop back from the singlet excited state to the ground state will come in terms of fluorescence. Okay, that will come in terms of fluorescence. There is another pathway that from the lowest excited singlet state, it will not come directly to the ground state, but somehow it will have an intersystem crossing to the triplet excited state. Okay, and because this transition is forbidden, this intersystem crossing occurs quite slowly. So the transition, whatever the relaxations are happening, the back path towards the ground state through emission of radiation will take a lot of time. So there will be a delay. Instead of rapid emission, there will be a delayed emission. So the emission will first follow the path from ground state to S2, S2 to S1, S1 to T1, and then finally from T1, it will come back to ground state, and this will be the phenomenon of phosphorescence. So this entire diagram is known as the Jablonski diagram. This is known as the Jablonski diagram. Okay, so here is the explanation. At the ground state, the molecular orbitals, they are occupied by 2 electrons and with antiparallel spins. So total spin of the molecule is 0, and this is known as the singlet state, and it is known as S0. When it is in excited state, the electron spins are in excited state. So if you have an excited state S1 or S2, this will be antiparallel. Okay, there will be first one parallel like this and another antiparallel. In the triplet state, the spins will be parallel. Okay, in the triplet state, the spins of the electrons will be parallel. Now, what happens? Activation and deactivation. How does that happen? So when you are absorbing a proton, okay, then the molecule gets excited from the ground state to one of the excited states, and this is first process is known as excitation or activation. This is governed by the Franck-Condon principle. This is governed by the Franck-Condon principle, which means that the electronic transition takes place so fast that the molecule does not even vibrate. Okay, molecule does not even vibrate because the nuclei, they move very slowly because of their masses, and this is in comparison to electrons. Now, how does this kind of activation get deactivated? So they can be categorized into two groups. One is a non-radiative deactivation, another is a radiative deactivation, which means that when from the excited state it is coming back to the ground state, it can either emit the radiation or it cannot emit the radiation. Now, what about photoluminescence and its relation with structure? So, if you have an aromatic ring like a benzene ring and you have a substituent on it, it will favor the fluorescent behavior of the molecule. Similarly, if you have lots of halogen substitutes, they will tend to decrease the fluorescence and they will shift the bands to longer wavelength. And this effect will increase if their substituted halogen has an increased atomic mass. Similarly, photoluminescence is also dependent on structure. So if you have a large number of fused rings, okay, large number of fused rings, they are found to be fluorescence. And even number of rings in a molecule also determines the extent of fluorescence. If the molecule is more rigid, the fluorescence is more prominent as compared to fluxional or flexible molecules. If the structure is more rigid, then it is more favored. For example, you can see fluorescein here, phenolphthalein here. Phenolphthalein is a very popular indicator in acid-base titrations. Okay, it gives a pink color. Okay, it gives a pink color. Similarly, many kind of fused ring systems you can also see here. So these will all be favored because of their structural rigidity. Also, if you have a large number of electron donating groups like NH2, OH, OR, and OCH3, and they are in conjugation with pi bonds with rigid cyclic kind of structures, then the fluorescence is much more prominent. But if you have electron withdrawing groups like COH, NO2, N double bond, and bromine iodide, these will tend to reduce it. Also, non-rigid molecules, they do not exhibit fluorescence much because they rapidly lose the absorbed energy. Okay, if you have too much flexibility and you're absorbing some radiation, you do not capture that radiation sufficiently, rather you come back to the ground state through vibrational relaxation. Okay, some kind of rearrangement of the vibrational energy levels will be taking place, and because of the fluctuality of the molecule, they will undergo either degradation or they will undergo vibrational relaxation. So they will not absorb that much and they will not either emit back the radiation, so they will have non-radiative decay. So these are again some examples which show fluorescence. Now, what enhances phosphorescence? If you are having certain paramagnetic metal ions which have copper and nickel, okay, if you have copper and nickel, then they can enhance the phosphorescence. Okay, if you are also having a molecular structure, like if you're having cyclic, polycyclic hydrocarbons, and they are having substituents like CH3, NH2, OH2, COH, OCH3, and which have lifetimes in the range of 5 to 10 seconds for benzene derivatives and 1 to 4 seconds for naphthalene derivatives, then you can get a strong phosphorescence. Also, if you're getting an electron withdrawing group like NO2, then that will diminish the intensity of phosphorescence. Okay, in phosphorescence. So what are the common factors that affect both fluorescence and phosphorescence? They are temperature, pH, dissolved oxygen, and solvent. So temperature, how does it affect? If you're increasing the temperature, the fluorescence decreases a bit. Okay, it always decreases a bit because this temperature is causing the viscosity of the medium to change, and also it will change the number of collision of the molecules of the fluorophore with solvent molecules. So if it is increasing the number of collisions between molecules, then again the deactivation by internal conversion and vibration relaxation is more. So our major interest, it lies in the fact that from the singlet excited state it has to go to the ground state, and thereby there will be a radiative decay. If there is a radiative decay, it will be either resulting in fluorescence or phosphorescence. But if the temperature is increased too much, the solvent molecules are interacting too much and they are crowding around the groups, then what will happen? They will undergo some vibrational relaxation, or in between the singlet excited states the decay will occur and they will lose all the energy, and thereby they will not emit the radiation. So as a result of that, the fluorescence will decrease. Similarly, pH. So they have given some examples how pH can result in fluorescence emission. For example, if you have serotonin, okay, if you have serotonin, so in neutral pH, the fluorescence emission maximum is 330 nanometers. Okay, the fluorescence emission maximum is 330 nanometers. But if you have a strong acid, then the fluorescence emission maximum is at 550 nanometers. Okay, it is at 550 nanometers. Also, in molecules containing acid or basic functional groups, changes in pH of the medium can change the degree of ionization, and this will also affect the extent of conjugation or aromaticity of the molecule. Aniline shows fluorescence, okay, but in acid solution it will not show fluorescence because the conjugation will be affected, and it will be affected because of the formation of anilinium ion. Okay, so because pH control is so essential, that is why we employ many buffers during observation of fluorescence. Okay, now dissolved oxygen, you know, is paramagnetic. Okay, they're paramagnetic, and even if you have some transition metals which have unpaired electrons which can cause paramagnetism, then this actually promotes the intersystem crossing from singlet to triplet states. So if you have a longer lifetime of the triplet state, then radiation less deactivation may occur. Okay, it can also cause a large decrease in the phosphorescence intensity, because if the oxygen is in the triplet state, at the ground state, it will get the energy from an electron in that triplet state and it will get excited. So actually it will be the oxygen that will be emitting, but it will not be the phosphorescence. Okay, so dissolved oxygen should be removed from the system before proceeding. Similarly, you should be very careful about the kind of solvent that you are taking because it will affect the hydrogen bonding ability. Okay, solvent polarity, viscosity, heavy atoms in the solvent should also be noted. So, because they can affect the fluorescence and phosphorescence. If you are taking a solvent of increased viscosity, that is favorable because there will not be too many perturbations in the solvent, not too many associations in the solvent. So, the deactivation due to collisions in between the structural part and the solvent, that will be lowered, so that will increase the fluorescence. Similarly, if solvents do not contain heavy atoms, fluorescence is better observed, but if there is presence of heavy atoms, phosphorescence can increase. Okay, so there are two different kinds of effects for phosphorescence and fluorescence as regards to heavy atoms in the solvent. Now, what kind of instrumentation is there for fluorescence measurement? So this kind of instrumentation we can see. You can have a light source. Okay, you can have a light source. You can first see the absorbance and that will be passed to a detector. Similarly, the light source will pass through the sample. If the fluorescence is detected, then it will also pass through the detector. And then finally, we can see that how much is absorbed and how much is emitted. So the essential components will be some excitation light sources should be there, filters, monochromators, sample holder, detectors, and readout devices. Okay, this is the kind of arrangement for a fluorimetry. Similarly, for phosphorescence measurement, just the basic difference is that it occurs at a different time frame. Okay, and it is better if the sample is solid or at liquid nitrogen temperatures. So the basic instrumentation setup will be similar, but the sampling technique and the recording procedure will be different for fluorimetry and phosphorimetry. Okay, here the phosphorescence for the sampling technique, they need to be at cryogenic temperatures of liquid nitrogen. So the analyte needs to have good solubility and the solvent must be forming a glass-like structure. Okay, and it should be highly pure so that there will be nil background of phosphorescence. Usually ethanol is an excellent choice, okay, for polar molecules. Okay, and if you're taking non-polar compounds, then a mixture of diethyl ether, isopentane, and ethanol in the ratio of 5 is to 5 is to 2 is taken. This is commonly called as EPA. Okay, this is commonly called as EPA, and it is an excellent choice for non-polar compounds. For phosphorimetry, usually the spectrophotometer is also similar to that of a spectrofluorimeter, except that the first, like the for phosphorence, they have to be fitted with an extra recording device. This is known as a phosphoroscope. This is a rotating shutter device which is commonly known as a phosphoroscope, and the sample system, as we have mentioned before, has to be maintained at liquid nitrogen temperature. So this is an example of phosphoroscope. So you can see that the liquid nitrogen is present around the sample. Okay, and also it is silvered. The radiation is passing through this, and this will be the sample tube, and this is enclosed within a Dewar vessel, which means it is insulated from external perturbations. So this is known as a phosphoroscope. So phosphoroscope can also have variations. You can have a rotating can phosphoroscope. So this will be a hollow cylinder which will have slits which are equally spaced in the circumference, and the entire thing is rotating with variable speed. Okay, it is rotating with a variable speed. First, the sample is illuminated, and second, it is darkened. And whenever there's a dark phase, the phosphorescence radiation will be passed to the monochromator and will be measured. So this is a setup of the rotating can phosphorimeter. So you can see that the phosphoroscope is here and the entire thing is being rotated through a phosphoroscope can. This is the excitation shutter, and whenever the emission is detected, it is passing to the monochromator. This is the emission shutter. So this is how the recording system for phosphorimeters work. You can also have a rotating disc phosphorescope. Okay, the becquerel or rotating disc phosphorescope. It has two discs which can be mounted on a common axis, and this can be turned by a variable speed motor. Okay, so here also there is this. This is how the rotating becquerel system works. So here you have a phosphorescope, and here in terms of rotation it will not be there, but instead the becquerel discs will be rotated continuously, and so the excitation will pass through the slits to the sample and then to the monochromator. Okay, so the becquerel discs will be rotating instead of the phosphorescope itself. So this is a basic idea of the phosphorimetry and fluorimetry, and I am going to forward also a document to you which you can read, and this will be very helpful for you because lots of descriptions are given here, including everything that we have discussed. So I'm giving the link in the group. Just check. Okay, no, this is not the one. Haha, yes, this is the one. Yes. So the latest link that I have shared, you can get the PDF for fluorimetry and phosphorimetry. You read through this and you will get all types of hints. Okay. Yes, we can get the PPT and the PDFs for the earlier 2 days. I will share them tomorrow. Just remind me. Okay, just remind me. I will share them during tomorrow's class. So copy the link for the PDF for fluorimetry and phosphorimetry. You can this is not the same presentation, but it contains more extensive information than the presentation that we just saw. So for phosphorimetry and fluorimetry also, we are just touching upon these aspects today. So we have covered electromagnetic radiation, IR, UV, NMR, mass, fluorimetry and phosphorimetry, and we will move to further topics. You have a very vast course, so we will be touching on all the aspects briefly, and then if time permits we will touch on the smaller portions as well, and we will be discussing some more questions. Okay, we'll be discussing some more questions. So thank you. Make sure you have all the links for the different types of topics that we have discussed today: NMR, mass, and fluorimetry and phosphorimetry. Make sure you have noted them all down. So I'll be leaving the meeting now. Thank you so much. And I hope your understanding developed a little during the session today. And I hope during the subsequent classes also, you will be covering the portions, and it will be easier for you to read through the portions now that you have discussed in the class. Okay. So thank you, and please practice all the problems that we have discussed. For NMR, UV, IR, practice makes perfect. So it might appear very easy, but with complicated spectra, even till now, even with PhDs and postdocs, they are unable to solve the problems till now. So even in entrance exams, this keeps coming. So this will be very helpful for you in various competitive examinations as well. So wishing you all the best, and let's look forward to the next class and hope we cover a lot of portion tomorrow. Thank you and good night.